All right, you guys can see me? That is a little bit crooked. I don't like that. Okay, so if you guys remember yesterday, we took a iron nail and we put it into a solution of copper sulfate. We know for sure the iron must be involved in the reaction because when we looked at this reaction, there was the iron and then there was copper sulfate, and we always have to have 1/2 of each for the reaction to occur. If I just had copper sulfate and it was reacting with if I had just had copper and the sulfate, then what that would mean in theory is that this bottle of copper sulfate should be reacting on its own by itself. And we know that's not happening. It needs to be mixed with something. So that tells me that the iron is definitely involved in the reaction. We did some processing yesterday to figure out what was happening with the iron. We looked at this sheet over here. We had some color observations. We also had some reactions, and we found that iron was here, 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 and here. I got to be mindful about what these different irons are. So this is iron, the solid, which would be our nail. There's iron 2, which is aqueous, so that tells me it's in solution. There's iron 2 here, and there's also iron 3 as well. If we look at this other page, we can tell that when we're looking at iron 2, it is a pale green color, and iron 3, it's going to be a pale orange color in solution. Are we okay with that? All right. The other thing we wrote down were some definitions. So loss of electrons and gain of electrons for oxidation and reduction. Remember, Leo, the line says GER or oil rig to help you remember which one goes where. That's just regurgitating definitions. We've already identified the oxidation reaction because we recognize that the solid iron is reacting. We saw it was starting to change color already. And if I look at the reactions for my options, the only one that had the iron solid was going to iron 2. So that's why I selected that reaction here. We all okay with that? So the thing that we were stuck on that I was going to say, let's wait till tomorrow and see what we have observation-wise, is we were looking at the copper sulfate, and we were trying to figure out from the copper sulfate, is it the copper 2 ion or is it the sulfate ion that's reacting in this reaction? So let's just do some observations. Let's look at our sheet here. Now, copper, the metal, solid, is pink. Copper, the ion, Cu2+, is blue. So those are some things that I'm already starting to identify. And the last thing that we had was sulfate. So let's find sulfate on this list. Here it is. Sulfate ion, SO2-. So these are the things that I'm looking at as potentials. In particular, I know that I'm dealing with copper to the ion because we're talking about in solution copper, not solid copper, because this is solution. So I've already identified that basically what I'm trying to think about is it the copper ion or is it the sulfate ion, where you are, there you are, that is reacting. So let's look at some of our observations just to get an idea. So here is the beaker from yesterday. And we look at that solution, and we can also look at what's happening with the nail. Isn't that cool? So the nail obviously has some brown pigment, pinkish brown pigment forming. It is a solid. It's not rust, I can tell you that. The other thing I want to compare is the solution. So we know that the copper 2 ion is a blue color, like this. But when I left this overnight, we noticed that the copper 2, or sorry, I shouldn't say the copper 2, the solution is now no longer that same blue. So what does that then tell me? Do you think it's the sulfate, or do you think it's the copper 2 ion that has reacted? The copper 2. So I know that because of the observations that have occurred. The observations that has occurred is that I see that the solution is no longer blue. So that means I probably am losing my copper 2 ion. The other identifying feature is that I see that there is a solid forming, and that solid that's actually forming is copper. Real copper. So if you lift up your nail, you should be able to see hopefully some brown pink that is formed on top of the nail. This is also known as a displacement reaction, which I think you guys might have covered last year. So from that information and from what the evidence says in the observations, I know that the other half of the reaction has to deal with the copper 2. It is not going to be the sulfate, because the sulfate here is a colorless ion. And if the sulfate was reacting, I would expect the solution to have stayed blue. I also would have expected not to see any copper forming. So I'm using process of elimination to figure out which of the two in the copper sulfate is actually reacting. You see how we did that? Okay. So now that I know that, let's look at our reaction schemes to see where Want my pen? No, I don't. Let's see where the copper 2 is, so that way we can figure out what's happening. I do want to point out again, if the sulfate was reacting, if the sulfate ion was going to sulfur dioxide, we would have seen bubbles. Did we see any bubbles? No. So that helps me again rule out that the sulfate is not in the reaction. Sulfate's also in this reaction. It goes to another ion that is, if you look on the other sheet, should say colorless. Where are you? There. Colorless. So again, we wouldn't have expected a blue or the blue color to change if that was the case. So you can go through and you can troubleshoot it. You can, like I said, work your way through and see all the places that you see sulfate. And everywhere you see sulfate, the ion that's forming is also colorless or it's forming bubbles, and we haven't seen anything in our observations that suggests that has happened. Are we good with that so far? So that again confirms we are dealing with copper. So if we look through our list and we look for copper, I see copper right here, and I see we have the copper 2 ion going to copper the metal. Again, we have to think about what order is that reaction supposed to go into. So we started with the blue color. We've ended with a solid that is a pink brown color. So it's going in this direction. Now, since one half of my reaction is oxidation, the other half must be the reduction half. We always have to have them in a pair because I can't create or destroy my electrons. So we start as Cu2+, and then we go to Cu. This was aqueous. This is now a solid. So, good news. This is all you need for the achieved. 3 credits in the bag. You guys are going to love this. In fact, the merit and the excellence is also not too bad. And in fact, the excellence is kind of like a walk in the park. You guys are just going to love this standard. It is ridiculous how easy it is. Okay, so let's now talk about equations, and let's also talk about observations and how we link it. So we need to justify our results and how we know that this is a redox reaction and who's doing what. So let's start with the reduction half of the equation just to make sure that I've correctly identified this reaction and I have it the right way around. So I'm going to write my Cu2+ going to Cu. Now, something I have to be mindful of is this is a gain of electrons, and I have to be mindful of how many electrons are going to be gained. So when I look at this, I see that this is a +2 and it's gone to a 0. So in order for me to lose the +2 charge, we are adding 2 electrons. So on reduction reactions, the electrons should be on the product side because you are gaining them. Are we okay with that? All right. For the excellence, you need to put these 2 equations together into a full equation. So you're going to put these 2. The way you have to add them together is you need to check the electron number, and the electron number needs to match. If they do not match, you need to do some multiplication so that way they are the same number. In this case, these 2 are the same number, so you can go ahead and put them together. And when you do that, since the electrons are on opposite sides, they're going to cancel out. So let me show you what that looks like. I'll do the working down here just so you can see everything. So Fe solid becomes Fe2 plus 2 electrons. I personally like to align my equations by the arrows, so that's way easy for me to find everybody. Like that. Now, I check to see if my electron numbers match, and in this case they do, so I don't have to do any extra multiplications. If they don't match, then I would need to. So that cancels out with that, and then I just put them together. And when I put them together, that's my full equation. So I have Fe. You don't need the states in there. I'm just including it. I made a mistake here. That should be 2 plus, and that should be nothing. So you don't need the states. I just put them in there. Like that. So the full equation is required for the merit. Sorry, for the excellence. So I'm just showing you guys how to put it together. Oh, with that. Keep going. Oh, wait, yep. So let's go back to this page here because we need to start justifying how we know what's what. So we need a linkage to the observations. So explain how you identified oxidation and reduction reactions linked to the observations. So we first started with a gray silver metal, which we've identified as iron, and a solution of copper sulfate, which is blue. So the solution was blue because of the copper 2 ion. Then we got to think, so in the reaction, it started with a gray shiny metal, which was the iron, and a blue solution of copper sulfate, or you can say which was copper sulfate. The solution was blue because of the copper 2 ion. Sulfate is colorless, if you want to add that. Right. After they were added together, we saw a brown metal form, a brown pink metal form, and the solution changed to green. All right. The pink brown metal is copper. Which came from the C2 plus ion. And the green came from the iron 2. I should make this bigger. I'll make that bigger for next time. The green color of the solution was from Fe2 plus, which came from the iron. Let me zoom that out. So now I'm starting to link my observations to what I have, because we're using those observations to help figure out what's going on as a chemical reaction. You've basically already had to do the merit requirement in order to do the identification process anyway, because you were looking at the observations to help you figure out how you were assigning everybody. All right. Next thing is your justification. So identify how the oxidation reaction with the electron transfer. So Fe has lost 2 electrons to form Fe2 plus. Since it's loss of electrons, it is therefore oxidation. And then in the reduction reaction, we have copper 2 ion. It has gained 2 electrons to form the copper, and that is the gain of electrons is reduction. Sorry, reduction. So this bit here is the merit. So for the merit, we're looking for, do you have the observations and to justify what you were doing? Have you gave me specific numbers of electrons gained or lost? Have you given me the half equations for both of them? That's it. All right. I'm going to quickly talk about the excellence because I think it's also kind of crazy to get how these credits break down. So, can I move it? Got it? Okay. I will talk about this on Monday, which is using oxidation numbers to justify how you know which one's oxidation and reduction. When you guys actually look at the clarifications of the assessment, you are actually not required to do this. So for the clarifications of the assessment, you need to justify either using the oxidation numbers or the electron transfer. Let me actually pull it up so you guys can see it. That way you guys can be like, oh my goodness, it's so easy. There you go. Okay. Maybe zoom that up. Okay. So, some things to keep in mind of what we're looking at for the achieved, merit, and excellence. Achieved, you need to name the formula of the oxidation and reduction species and describe if the process is either oxidation or reduction with reason, so gain or loss of electrons or change in oxidation numbers. Yeah. So basically what you guys have done here, this is the identification. This is the justification, gain or loss. There's no specific numbers that you have to state for that for the achieved. For the merit, they want you to show in-depth understanding by balancing half equations and by linking these observations to the redox reduction with reasons. So you should be talking about the number of electrons gained or the number of electrons lost. So we have done that. You've done your observations with linkage. You have told me specifically, not just general, but how many electrons are they losing, how many electrons are they gaining, and include the half equations. So that is the merit. For the excellence, you need to show a comprehensive understanding of redox by linking balanced half equations, a correct overall equation, observations, electron transfer, or oxidation number. So you don't actually have to do oxidation number in order to get excellence. If you've done this in the merit bit, you're actually fine. So, what am I looking at? So the only thing that's really different between the merit and the excellence is adding this balanced equation, which is what I showed here. So even if you don't do this, you can still get an excellence. It's a very poorly designed assessment. Very, very easy. So that's it. That's all you gotta do. Wowie. I know. So there are going to be some extension lessons that I will give you guys if you want to learn the more complicated redox stuff. But for the assessment, I'm planning just to keep it simple because I'm very mindful that I don't want to unnecessarily trip you guys up. There's a lot of other chemicals we could do. So this is the big debate on the teacher forums. So you see how there's a lot of things in here that are not as simple because they have like oxygen involved as well, like dichromate or permanganate and stuff like that. In theory, and this is the unofficial kind of rule that the chemists have, is that we should give you equations with this, so you have to do the more complex balancing. But when you look at the clarifications, there isn't actually a requirement to do that. So I'm going to be nice. I'm not going to include that. However, If you want to aim for top scholar in level 2 chemistry, I want you to be able to do it, because that to me is what makes you the top of the class. So if you're aiming for that, I will provide some extension work so you guys can show me that you can do those equations. But when it comes to the actual assessment, I'm going to keep it simple and not do those complicated ones, because it's not required in the assessment. So why should I make it harder than it needs to be? The other issue that I have with putting in the more complicated ones is that students often make mistakes on them, and it actually requires you to understand additional material that's at the merit and the excellence level in order to do the achieve stuff. And that to me means that the assessment is not well designed. If you do the oxidation number stuff, you'll see. But for example, dichromate here and the chromium ion, where'd you go? CR. Help me find CR, guys. CR, there. So you see these two right here? A lot of people get this the wrong way around when it comes to the redox reaction, because you need to actually understand oxidation numbers in order to do that one correctly. I think that's really unfair for me to give that as an assessment question if you're just aiming for achieve, because you're now accessing something that is required for merit or excellence, and even then, it's not actually a requirement, because when you look at the clarifications, it says or. So electron transfer or oxidation numbers, electron transfer or oxidation numbers. So to me, that, because the assessment clarifications and the design of the assessment is kind of wonky like that, I don't feel that that's fair for the students that are trying to aim for achieved. It's also a very restrictive assessment in what can get for merit, because they want you to have both half equations balanced. And if I give you two hard ones, then if I give you a hard one, then it really makes it extra challenging when I don't need to do that. So just kind of letting you guys know, FYI, that I will be kind on the assessment. But if you want to be top scholar, I want to see these complicated equations being done. Okay? And that's basically it. It's pretty insane how this is worth 3 credits. The titration's worth 4 credits, and that was way more work. And the ion identification, again, worth 3 credits, but is way more work. So it's a very strange assessment, but it should be a nice, easy 3 credits for you guys. Okay? And I think we can probably do the first attempt next week. All right? So what we're going to do for the remainder of today's lesson is I have some different chemicals set out so you guys can actually do some redox reactions and practice writing on the template. The ones that I have selected are a little bit harder, so just keep that in mind, and we will work our way through them as well. All right, you guys can clean up these guys. You're welcome to take a photo because it is pretty cool. The copper sulfate can go down the sink. Give it a good rinse. Give the beaker a good clean as well. And then the poor nails look like they have, let's see how bad this is actually. Come on out. Oh, it's really dissolved it. No, not dissolved it, really reacted. Look at my nail now. Oh, you can't see there. Hold on. It's lost. So we're not going to keep these nails because I don't think that's worth keeping. So we'll just chuck these guys out too. But isn't that cool? It's so small. That's why I only want you guys to dip half the nail in there, so you can actually see how much actually reacted away. So remember, it's not dissolving. It has displaced it with copper. So now we made copper. Do wash your hands if you just touched it like I did, because you don't want that copper sulfate. All right, cool? All right, let's do some more.